Hello, everyone, and welcome to today's webinar. This is a joint webinar between the ASQ Quality Management Division and Inspection Division. Today, we have the pleasure of hearing from Michael Down on the presentation of MSA, the most important core tool. You will be receiving an email 24 hours after this webinar documenting your use. You will receive this in a form of email. If you don't receive it, please feel free to reach out to me, and I will be able to give you a certificate if you don't receive the email by any chance. Michael Down, he's a senior consultant of Omnix. He has extensive engineering quality and reliability experience. He has 40 years industrial experience, 32 years with GM. He also represents GM as SAE and at IATF, responsible for global automotive standards development in the areas of quality and core tools. So please welcome Michael Down.
Good morning, everybody. Today we're going to talk about the MSA being the most important core tool. The reason that I say that, a lot comes from the training and time I spent with Dr. Deming when I was at General Motors. I had the opportunity to work with Deming between 1985 until his death in '92, and it was a great pleasure. Some of the things that Deming said was, in God we trust, all others bring data. Without data, you're just another person with an opinion. And if you can't describe what you're doing as a process, you don't know what you're doing. So all of these require data and information, and that data and information comes from measurement. So out of the core tools, I feel that MSA has the most important role to play. If we look at each of the core tools, we start out with APQP. It relies on data evaluation through every single phase. That data evaluation makes an assumption that the measurement systems are good and have very minimal error. A lot of times management assumes all data is 100%. Having a master's degree in statistics, I know that there's nothing that's 100%. There's always some level of error. If we look at FMEA, especially for the process FMEA, it relies on data and data collection. It relies on measurement systems and measurement equipment giving us the right data and information to be able to make the product that our customer requires. In a DFMEA, as we're developing the design, we're doing a lot of validation testing and evaluation of parts, again, using measurement systems. And on the side, from my experience, the worst gauge R&R values that I ever came across were normally with design lab equipment, usually because the measurements that are done in engineering development are done infrequently, where in manufacturing you're measuring all the time. So you start to notice if you're having issues. In the design case, you don't. And that's a big deal because the design engineer is relying on that information to make critical decisions about the design. We look at the SPC core tool. All the information that's evaluated in SPC is coming off measurement systems. Now, once we have a control chart that's running, we should be able to see indications of measurement issues, but again, SPC is relying on measurement systems for the data. And then PPAP, the final submission, our part submission for approval from our customer, requires evidence and artifacts that our data is accurate and precise, and in giving them the information that they need. our major requirements that we have in relation to ISO and IATF all directly look at areas of measurement. In ISO 9001, what needs to be monitored, methods of monitoring, measurement, analysis, when is it monitored and measured, all of these are critical. ISO 26262, which is functional safety, relies on the ability to react to data and information that's being collected off some type of measurement device or measurement system within a circuitry. And IATF 16949 has clauses, specifically 71511, that specifically calls out measurement system analysis. So in all those areas, it's critical that we have a system of measurement that's reliable. At what time should measurement be considered? In reality, measurement of a part starts right at the conception of the design itself. So as we start to develop the design, the product engineer, understanding the function of that part, is going to put information down in the CAD or print area of how's this part going to be measured. The engineer, knowing the application of the design, establishes datums to secure where that part's going to be held and how it's going to be measured. And all of this is through geometric dimensioning and tolerancing. There was a period of time where companies started getting away from GD&T, and the problem when you do that is that then if the manufacturing and quality people don't have direction in relation to how the part's going to be measured, they'll do it the way that they need to do it for whether it's being manufactured, or the easiest way it is to clamp it to measure it from a quality perspective. So it's very critical that the product designer establishes how that part's going to be measured. They also, at this point in time, at the conception of the design, are identifying key product characteristics, again, telling manufacturing and quality what points of the part are critical that need to be measured and need to be held to a certain specification. So again, without this information, it would be left for quality and manufacturing to develop how they're going to measure the part. Going through an example, when I first started working at General Motors in Lansing in the engine plant, it came to our realization of how critical datums are. If you look at this example with the engine block, the datum for an engine block, all the characteristics that are in the engine block, the cylinders, the cams, everything else, are all related back to the datum, which is the crank line. But when they're manufacturing the part with all the dimensional information being related to the pan rail. Pan rails where they mount the oil pan on the bottom of the engine block. Why was that done? Well, because it was a flat space, and when you put that flat space on a manufacturing rail, you can just slide that heavy engine block down the line. Now you can see how that could be an issue if the datum is actually the crank line, and the pan rail actually has to become a critical characteristic of the engine block, or then when it's being measured and being manufactured, it's going to be done incorrectly. So it took a while to come up with a solution to this, but when I first started working at the engine plant, everything was being manufactured to the pan rail. So what's a measurement system? Measurement system has some level of input, some operation and output. The key process output variable is a deliverable of information that's used for making a decision on the product, process, or service. So trying to not just focus on the gauge itself, but to focus on the whole measurement system is what's important. is that there's some level of input, some output, and some operation that potentially could be done on the product. From the definition, it follows that a measurement process may be viewed as a manufacturing process that produces decision via numbers, data, and its output. So we have some process that needs to be managed. We take some measurement. There's some value that's created, and then somebody makes an analysis of that information, and a decision's made. So in all those areas, there's potential for risk and error. Looking at this measurement system example, to measure the outside diameter of the tube, we use a system that includes the item of interest, the part that we're measuring, the person who's taking the measurement, so there's some person that's involved, the method to use the equipment, in the environment where the measurement is being performed. Do we have proper lighting so they can see what the increments are? As a result of this activity, we make a decision based on the value that represents the diameter. Now, you can see a lot of issues that could occur with this example in relation to how the scale is being held, the number of increments that are on the scale, the point that they're taking the measurement. They could take an infinite number of measurements of diameter by rotating the tube. So once we get this measurement knowledge is obtained, we say, well, how big is the measurement variation? Do we have so much measurement variation? Is it capable for the usage that we're going to be using for the data? Is the measurement system stable over time? That's probably one of the most overlooked analyses of measurement systems is measurement systems can be unstable, where you get unstable results. I had a person that worked for me in Lansing that was checking all of the gauges that were coming into the 3800 plant and found out that 1 out of 10 of the gauges that were coming in fresh out of the box were out of control. They're unstable, and he returned them. And there was something that was incorrect in the gauge when it was assembled that caused it to be unstable. Again, what are the sources of measurement variation, and how do we improve the measurement system to make it better? Measurement system is a process of test and method and specification. Again, it's personnel, the operators, how have they been trained to use the gauge, their ability to use the gauge, the tooling equipment, the gauges, fixtures, test equipment, and calibration. I would say over 30% of the issues that I had with problems in manufacturing turned out to be fixturing problems with the gauge. The biggest fixturing problems that I found normally were in coordinate measuring machines. I found a lot of issues with Zeiss coordinate measuring machines where you had this very expensive gauging system and you had a poorly executed fixture. Or they were over-clamping the part. So clamping, pressure, fixturing, that's all put together. But before I would ever start to do any level of problem solving, I would always evaluate the gauging system for gauging variation, and I would focus on how the part was being fixtured, going back to the print to see what datums were defined by engineering. What items going to be measured, the part or the material sample measure, the sampling plan, etc. We're not going to get into it in this presentation, but because measurement error is only one piece of the frame of what could impact the sample and the results of the sample. If I'm doing a data collection, how I collect that sample is also going to impact the results and what direction I take to make improvements to the process. But we're not going to cover that. That would be in like statistical process control. And then environmental factors, temperature and humidity. Again, over the years, this became such a big issue. At GM, I had them buy me a portable machine that would measure temperature and humidity during the test I'd be running out in the plant. I found a constant issue with temperature and humidity when it comes to measurement, especially when you're getting down into the microns. So what is MSA? MSA is a measurement system analysis. It primarily deals with analyzing the effects of measurement systems on measured values. The objective of MSA is to assess the quality of the measurement system. In actuality, if you go through the whole MSA manual, it covers a lot of other areas in relation to the tracking back to standards, the traceability of our gauging systems, the purchasing and validation of gauge and measurement suppliers. A lot of that information is covered in the MSA manual. So MSA is the control of gauges and fixtures. The proper qualification of gauging and test equipment requires the use of statistical procedures to analyze the inherent variability observed in the use of this instrument. So some method needs to be used to try and qualify whether there is a minimal amount of measurement error. So additionally, before capability can be, the study can be performed on any machine or process, you need to validate and qualify the measurement system. As you can see in the diagram, when we're looking at this data, the data is a mixture of the actual process variation and the variation error that's being created by the measurements device itself. So what occurs is we have these red zones that, if we have measurement error, could potentially cause us to make the wrong decision. We could make a decision that a part is out of spec when it's actually in spec, and we can actually make an error where we say a part is in spec when it's actually out of spec. So the idea here is there's two ways of reducing overall variation. We can either improve the process, or we can reduce the measurement error and improve the measurement system. So anytime I went into a problem situation, the first thing I would do is evaluate the measurement system to make sure that my measurement error wasn't what was causing the problem. And normally it's a lot cheaper to make improvements to the measurement system to reduce the measurement error than it is to make process improvements. So I'd usually start with the gauging system first. So the best-in-class approach is determination of these fundamental issues are most meaningful if made relative to process variation. If you are familiar with using gauge R&R, for example, or gauge repeatability and reproducibility, it gives you an option to either compare the gauging error to the spec range or in relation to the process variation. In reality, it's better to do it to process variation because, especially if you start reducing the process variation under 50%, you may get to a case where your measurement system is not effective for that reduced variation. So you may get it where it's acceptable for the range of the specification, but not acceptable for the reduced variation in the process, which then makes it an issue in relation to doing statistical process control and continual improvement of the process. So I'm not going to go through all of this in detail, but in general, the statistical properties of measurement systems start out with discrimination and uncertainty, and then bias, linearity, and stability, the variation, which is the gauge repeatability and reproducibility, and then if there's attribute measurements, that's an additional area of analysis. So if we had a lot more time, we could get into more detail of all this information. Again, when we're talking about measurement systems, again, I like to highlight the IATF 16949, the 7.15 sections 1 through 3, all are related to measurement systems and the importance of understanding the measurement system. So the biggest thing to accept is that measurements is not always exact. When somebody's presenting information at a meeting and they're telling you these are the results that they got on their study and are recommending that changes be made, you should ask them what the measurement error was in the device that was used to collect that information. A lot of times we sit in meetings and just blindly accept data that's presented, assuming that there's no error in the measurement device. And it's really, I would be concerned if a person couldn't tell me what the measurement error was. When we look at measurement error, it can be classified as, first, if we have a gauge where there's a dial or some type of measurement that we have discriminating tick marks on it, then the discrimination could be an issue. Then the other breakdown is location. Location is broken up into bias, linearity, and stability. And variation is repeatability, or what would be considered basically the device's repeatability itself. Reproducibility talks about the measurement system's interface with the operator, and is there any issues with the interface between the operator and the gauge. So again, this gets into discrimination or resolution. This used to be a big deal years ago because most of our gauges had dials and indicators on them. You don't see it as much today. Even calipers and are digital, and they went to digital to get rid of a lot of this discrimination issue. But if you have a gauge where there are marks on it that are being used for discrimination, there are rules for how many marks and discrimination you should have. So I'm not going to get into that. If you have a gauge, you can check into that into the MSA manual. Measurement's not always exact. There could be some level of bias, a difference between what the gauge is telling us the value is and what the reference value is. Usually this is the reason that we master, calibrate our gauges at the beginning of a shift, is to see if there's been any shift in the gauge or bias of the gauge, and we make an adjustment to zero the gauge out. Now, what should be done is bias should be something that's tracked over time. A lot of times we think we resolve it by just having somebody master the gauge in at the beginning of the operation, but if you have to do that frequently, that becomes an issue. That there's some problem with that gauge, is if it's drifting. I would expect it not to be needed to be adjusted for bias for a period a couple days or so. It's every single shift it seems to shift. It could be an indication of a problem with the gauge. Linearity is looking at bias over the extent of the operating range or the specification. As I go across the specification, I shouldn't see a change in the level of bias. Linearity is what I've seen over my experience is that you don't see as much linearity issues with mechanical gauges as you do with electronic. So I have an electronic gauge in the plant. I'd really want to look at it for linearity. Mechanical gauges don't seem to be as having as big an issue with it, but electronic devices, especially when they're in the plant environment and the plant environment has a temperature that's not controlled, you could have issues with linearity. Probably one of the bigger ones that gets overlooked is stability. Over the years, I've seen a lot of examples where gauges had very good gauge R&R values, but didn't have, they were unstable. When you look at gauge R&R, look at gauge R&R as a single point capability analysis. It's not going to tell me how that gauge is going to operate over time. It's just telling me how that gauge was operating at that time I did the gauge R&R. So there are some gauges that have problems that you can't pick up unless you do a control chart on the gauge. Normally, control charts on the gauge where I take some master and I put the master in several times. So like at the beginning, I'm getting ready to pull a sample. I take the master and I put the master in 3 times and take the recording of those 3 measurements and put them on a control chart with an average and a range. But that control chart, I would do stability checks, especially on key characteristic gauging. I wouldn't do it on all gauging, but especially it's important to do it on gauges that are measuring key characteristics. Again, you would read the control chart. The control chart for this example doesn't really show what gauging control chart looks like, because it looks pretty flat. And there's not, there could be some hugging of the center line. There could be some cases where there's a lot of zeros in the range. It's not as pretty as this chart. So, but you would do it on a control chart, and you see some point that was out of control, you would evaluate the problem. Repeatability is just taking multiple measurements on the same part, and that's why it's called equipment variation. Repeatability can be done really quick on gauges just to check and see if the measurement system can measure the same part and give me the same results off the same part multiple times. So it's called the equipment variation, and the other part of it is reproducibility, and that's where we're having different inspectors or appraisers measuring the same part several times and seeing if there's differences in the different appraisers. What you should see, like in the diagram that's on this slide, is A, B, and C should line up fairly close. If they start to drift apart, then that's when you normally identify there's some issues. So if I looked at that, it looks like A is getting a little bit different readings than B and C. But that doesn't mean that A is wrong. It could be that A is right and B and C are wrong. So you never know. But we use this information with any gauges where we're having operators that work with the gauge. Now, as a side note, when you look at gauge R&R, there's 3 operators. The reason that was set up for 3 operators is most of the plants were running 3-shift operations. So you had an appraiser on the day shift, an appraiser on the afternoon shift, and an appraiser on the midnight shift. Now, if you're doing a gauge R&R, you would have to have somebody run the the day shift gauge R&R with the day shift appraiser. Then you'd have to go to afternoons, and you have to go to midnights, and then pull the information all together. Gauge R&R is gauge repeatability and reproducibility studies are pretty intensive and take a lot of time, just because of the logistics. So ideal measurement systems produce correct measurements each time used, and each measurement agrees with the master standard. We have the statistical properties of zero variance and zero bias, consequently zero probability of misclassifying any product measured. So in saying that, there are not many ideal measurement systems. Normally, we're looking at measurement in relation to accuracy and precision. We'd actually like to have it both accurate and precise, or in the center of the target. So accuracy and precision. So we look at accuracy and precision. That's normally what's evaluated when you have somebody come in and certify your gauge. So when there's a label that's on the gauge, if you're going to if you're auditing a company and they have a placard on the gauge that said it was certified 2 months ago, it's normally certified for accuracy and precision, and so it's not part of the gauge R&R analysis. It's part of a normal maintenance of the gauge in a normal review of the gauge. So in most cases, I'm assuming that if a gauge has been certified and hasn't been moved, that its precision and accuracy have been established by some internal or outside source. There's a bunch of different areas. We talked about repeatability and we've talked about reproducibility, but there's many different factors that can impact measurement system. And I know this is kind of an eye chart, but this shows a breakout of the different materials, measurement, environment, methods, and machines that can affect the actual results of the measurement. And so I really stress that gauge R&R is a very minimal level of analysis of a gauge. That as we look at gauges and we look at measurement systems, we should be thinking, how is that measurement going to be used, and where is the measurement system going to be placed when it's put in the plant? A lot of gauges that we had at GM eventually ended up in a gauge crib or an enclosure because of the impact of measurement of environmental temperature and humidity on the measurement. There were cases where I was called in, one example was for a turbine fuel pump where they had a auto compensation system that was supposed to make it so that they were running around 60 to 50% of the tolerance. And they were running 120%, and they wanted my help. What I told them to do was to run the process with and without the auto comp turned on. And what it turned out was that when the auto comp was turned on, it was running 120%. When it was turned off, it ran 60%. The auto comp was auto-compensating, overcompensating. So you had an overcompensation, which was causing it to have more variation than it needed. Now, that is a measurement device that should have been evaluated in relation to the environment that was going to be placed in, because what eventually was found out was that there was the cutting fluids and everything was impacting how the part was being measured. So again, environmental effects on data is temperature could cause expansion and contraction of the part. You think about a piston that's made for an engine, it's made out of aluminum, and they're machining it down into microns. I know when I first started working at GM, they didn't understand the impact of temperature, so I took a piston and put it in a coffee can with ice and then put it in a gauge and held it with my hand, and when the column gauge, it actually moved a whole foot on the column gauge just by warming the part up. If I have poor lighting, it could affect my ability to read the gauge or use the gauge. I mean, I've been in some plants where it seems like you're walking into a dark cave and they're trying to do measurement in that location. It's not very effective. Glare could cause false reading, time effects on the material, humidity, contamination, vibration. There's a lot of work that's done when you put a Zeiss coordinate measurement machine in a plant where they isolate the whole enclosure so that as forklift trucks drive by, it doesn't cause vibration that affects the measurement. So we look at the measurement system, the equipment. How does it affect the data? The type of measurement equipment must be appropriate. The increments and the divisions must be smaller than the specification. The accuracy and the precision of the equipment could affect how good the data is. Bias linearity, the repeatability and reproducibility, and the stability of that gauge. So all of those we need to be concerned about and focused on. We can't overlook the fact that proper work instruction. I'm going to be talking about an example at the end of this presentation that will highlight that, but you have to have good work instructions. You have to have visuals. There's got to be a set procedure in relation to how the gauge is being used, how it's calibrated, and how the samples are prepared or need preparation before they're measured. If a national or international industry or profession accepted methods are not used, the organization must validate any documentation created or revised. Any of those things have to be approved by a customer. You can't, normally you've got to be following national standards to international standards to get into manufacturing nowadays. So there's a lot of different ways the tests are done, different types of measuring tests. You have shear tests, wire pull tests, dial indicators, high-powered microscopes, X-ray and thickness gauges, comparators. The list goes on and on and on. So from a mathematical perspective, we're looking at the level of trying to, what you're really trying to do mathematically is separate out the actual process variation from the measurement variation. And that's the challenge you have from doing the analysis. So you're looking at the difference between the mean of the total that's, what is the actual product mean and how much of the mean is being impacted by the measurement system. And then variability is the same thing. You have this total variance of the output of the data that you're evaluating, and there's a portion of that that's the product and a portion of that that's due to the measurement. You can use manual type statistical methods. You can use the analysis of variance method. You could use design of experiment to evaluate measurement system. And again, these measurement errors can affect the capability analysis, and this again affects the information that goes into PPAP. And this chart shows you how gauge R&R is impacted by how the gauge capability is impacted by the gauge R&R. And you'll see that's the reason they are trying to stay between the 10 to 20%, because as you start getting the 30, 40%, 50%, your error gets to be so high that you really don't have an effective capability number. So when we go into evaluate a measurement system, we're concerned about that bias and linearity. We're concerned about making sure that the capability of the gauge is good, the gauge R&R is good. We want that gauging system to be stable. We need to have that all in place before we do the capability study. The capability study should never be done with gauges that have high gauge R&R numbers. It's a waste of time. So here's an example. When I first started working at Oldsmobile, my manager, I taught him how to do statistical process control. And he called me up on the phone. He says, Mike, I must not have been listening close enough. I did my control chart, and every single point on my average chart is outside of the control limit. So he didn't have a single point that was in the control limit. So I went to his office, and when I looked at the control chart, the points that were on the top were from day shift. The bottom one was from afternoon, day shift, afternoon, day shift, afternoon. So all of the points above the upper control limit were from the day shift. The ones that were below the control limit were from the afternoon shift. So then when I went to the plant, now again, remember, this is coming off of a crankshaft bearing. So this is the crankshaft main bearing, so it's not an insignificant characteristic. They were using this column gauge where there's a bobber that floats on air, and as the part gets bigger, it restricts the air. So what it means is more air can go into the tube, so the bobber would go up. As the part would get smaller, it would let air escape around the part, so then there'd be less air going to the tube, and so the bobber would go down. So I talked to the guy on day shift, the inspector on day shift, and I said, how do you use the gauge? And the person on day shift said, well, I do it at the top of the bobber, so that would be the A point. And he said, Mike, I want you to tell you something. Every morning when we come in, those guys on afternoons are screwing with us because we have to reset the process. And they said, oh, okay. And so then I went to afternoons, and the afternoon guy said, yeah, I use the bottom of the bobber, so he's point B. And he said, Mike, I want to tell you something. Every time we come in, those guys on day shift are screwing with us. We have to reset the gauge every single time, reset the process every single time. And so then I talked to the supervisor, and the supervisor, I said, well, how are they supposed to be using this gauge? And he said at point C. And the way that we resolved this problem is we put a picture up and said, take the measurement from here. It was a simple solution, and immediately the process became stable. So it's very critical for measurement systems. Every company that I've worked with has had examples that are similar to this. So I mean, it's not something that's unique unless you have a very good company that's focused on looking at measurement systems. They tend to get overlooked. They tend to get people tend to have too high of expectations in relation to how good the gauging and measurement system is. So in closing, I'm going to close using one of Dr. Deming's quotes. It's not enough to do your best. You must know what to do and then do your best. If I have a bad measurement system I can be doing my best to make things better and actually making no improvement at all. So in saying that, I'd like to say thank you, and if there are any questions, feel free to ask. And I'll turn it back over to